Burkhard Herr and Alfred Mausner, the Krusell-Smith algorithm and overlapping generations. Hello and welcome to this presentation of chapter 10.2 from our book Dynamic General Equilibrium Modeling. In this chapter we solve the business cycle dynamics for the business cycle dynamics of the income distribution. So we look at an overlapping generations model and derive the cyclical properties of, let's say, the Gini coefficient or the bottom income quintile with output, with production. And I will show you how to compute this using numerical methods that Alfred Mausner and I present in our book Dynamic General Equilibrium Modeling. Now this application is taken from the third edition, which we are planning to bring out at the end of the year 2022. It's just mildly modified from the one in the version of the second edition, and you find a description of this little bit more sophisticated model in our online material. In the next 5 to 10 minutes, let me motivate this chapter, our results, the computational techniques that we use. Let me point out to you where you find all the materials. For example, you find Python code or Gauss code, as you like, on our download page, and how you perhaps may use this code to build your PhD paper. So I will also present to you a paper idea. So let's skip into the slides, which are also provided to you on our download page here. Now there's behavior of the income distribution, that's cyclical behavior in dynamic general equilibrium models has been probably studied. Yeah, the first ones who did it were Castañeda, Díaz-Jiménez, and Rios-Roll in a Journal of Political Economy article in 1998. And we will compare our results to their results. They looked at an infinite life households, and what's new in our application here is that we also use the Krusell-Smith algorithm, but for individuals who have finite life. And we will argue that this helps to explain the cyclical behavior of the income distribution. Now, in recent times, we have some papers, some results from Krüger, Mittmann, and Perry, or Kaplan, Mittmann, and Violante, which study a particular episode, a particular recession, a particular period in time, which is a Great Recession 2007-2009, which originated in the housing market, a subprime crisis. And they study the wealth and income dynamics. For example, the wealth inequality decreased in 2008, and Krüger and Mittmann-Perry provide a model that helps to explain this fact. And while Kaplan, Mittmann, and Violante also study the housing wealth in their model, which was one of the driving key parameters, key variables during this recession. Now we'll first present to you our results and motivate the paper. Then I show you the overlapping generations model that we compute. And then importantly, I will present to you the Krusell-Smith algorithm, which can equally applied to overlapping generations model. So that's one of the main points here in this presentation, how to apply it, how you have to extend it if you not look at infinitely lived households, but rather on households with finite lifetime. In our case, people do not get older than 90 years, for example. So the research questions which we consider is first cyclical income and wealth distribution. How can we model it? So therefore we need a stochastic overlapping generations model, because we have learned that the high inequality in the wealth distribution, well, it's much easier to explain it if you have life cycle savings in your model, and therefore you need finite lifetime. So people at age 50, for example, have much higher wealth than people your age at age 20 or 25 or 30. And to model this, you of course need the lifetime, finite lifetime. Now, how can we compute it? Well, there are basically two methods, and both methods are presented in our book, Dynamic General Equilibrium Modeling. One is that we use some perturbation methods. You may know this from the representative agent model, the standard business cycle model, which builds on the Ramsey model, and you might use our uh, our programs to solve for the solution, or you might use Dyna programs. So there are standardized softwares available. These standard perturbation methods, we will present them to you in our chapter 2 of our book and also in chapter 10.2.1. But realistically, you can only apply them to models without idiosyncratic uncertainty. So where the income of the individual may depend on aggregate variables, but its relative income with regard to other households is deterministic. Now, once you have this more realistic feature in your model that you have idiosyncratic uncertainty so that you may move up or down in the income ladder here, well, then these methods kind of break down and you have to use, well, in our view, there's only one option, and that's the Krusell-Smith algorithm, and that's what this presentation is about. So if you want to introduce the realistic feature of idiosyncratic income uncertainty, that you may move up and down the income ladder, that you have income mobility, in other words, well, then you have to resort to the Krusell-Smith algorithm. We use an overlapping generations model, and what's the beauty about the overlapping generations model compared to, let's say, the infinite lifetime model or the Ramsey model, the neoclassical growth model? Well, you have life cycle savings. People at age 50 or age 60, they have higher savings than people at age 20 or 30. Wealth peaks around age 65, 70 empirically, and our model is able to replicate this fact. And therefore, we already have some heterogeneity, inequality in our model that is difficult to introduce in the Ramsey model. So that's one thing that's shown by Hackett, that once you have overlapping generations model, if you start from given inequality of income, well, the inequality of wealth is even higher in this kind of model. Very nice paper by Mark Hackett in 1996. And we also introduce uncertain lifetime. This is a very important impact on income and wealth dynamics. Well, if you do not know how long you live, you actually face the risk of longevity. So it's a risk to become very old, because in old age you might still need savings. So people with a high expected lifetime, they accumulate higher savings because they might need it for a very long time during retirement, for example, for uncertain medical expenses, which go up at the age 85, 90, which increase tremendously. And to ensure against this negative risk of a long life, you build up uncertain lifetime savings, precautionary savings, and these savings, of course, they yield a return and hence an income, which you also need to model the income distribution and its cyclical behavior and its behavior over the lifetime. We introduce uncertain earnings so that people who have, let's say, high productivity find a good job. They have incentives to work more because there might be a big recession ahead, let's say the COVID-19 recession or the Great Recession 2007 through 2009, where they might lose their job or have a lower wage income. And as a consequence, it makes sense for them to shift their labor intertemporally to the periods where they have a high wage income, a high productivity, and where we, for example, are in a boom. The model also features pay-as-you-go pensions, which is important to explain savings in our economy. If you get a high pension, for example, in most of the continental European countries, you get a high pension, therefore people save less. And in countries like the United States or in Great Britain, the pension replacement rates are lower, so people have to save a higher portion of their income to have good life in old age. So we model pay-as-you-go pensions. And we have endogenous labor supply in our models. So if we have, for example, a boom, wages go up. Well, the substitution effect, the incentive effects to increase labor is higher among the very productive people in the economy. So they increase their labor supply by a higher percentage. And this helps to explain why some income shares move up or down depending on our phase of the business cycle. Now, let me present to you the income and wage inequality in the United States. So wages have a Gini coefficient of 0.375. This data is taken from paper by Butia Rodriguez, Diaz Jimenez, Virginia Reyes Rule, and by Krüger Mittman Perry. Income is much higher concentrated than wages, so Gini goes up from 0.37 to 0.55. Remember that the Gini lies between 0 and 1, and if it's 0, we have complete equality. All agents have the same wage or the same income, and if the Gini coefficient is equal to 1, well, one individual owns everything. And as you notice, the Gini coefficient of wealth is much higher than the Gini coefficient of income or wages in the United States, so it's around 0.8. And our OG model, well, it replicates the inequality in part. So we have wage Gini coefficient of 0.3, gross income of approximately 0.39, and wealth of 0.56. So it's a little less concentrated. Wages, income, and wealth are all less concentrated than empirically. And the main reason is we leave out the very top income earners, very top wealth holders. So we do not have the Elon Musk in our model. And for this reason, we do not capture the top percentile of the income and wealth distribution accurately. So interpret our model as a model of, let's say, the bottom 95% of the distribution. That's what we are able to measure in our model and to model and to replicate, but we do not model the top 1 or 5% of the income and wealth distribution. We do not have the very successful entrepreneurs in our model. In our model, we do not have self-employed entrepreneurs. And this provides us with the Lorenz curve of income and wealth. Here, the red line is the model. The blue line is the US economy, and the black line is the equal distribution, where, for example, 10% of the population, the poorest 10%, receive 10% of the income share. The lower bottom of the households, the lower 50%, also get 50% of the income share. That's the equal distribution. In the model, they receive something like 25% of the income, total income, and the income share, the empirical income share in the United States is less than 0.2, less than 20%. So as you can see, we do relatively well in the lower half of this Lorenz curve, but the top percent here we do not capture quite well. So for example, the top percent here in the United States has about 30% of income, while in our model it's just about 5%. So the top quintile, the top percentile here we do not capture in our model. And if you consider wealth, well, here again we have the equal distribution, which is the black line, where the Gini coefficient is equal to 0. The red line is the model, and the blue line is the empirical wealth distribution in the model. So we are unable to replicate, for example, the wealth of Elon Musk. Elon Musk, as of today, March 2022, he has something like 200 billion US dollars. That's his wealth, his net worth, a little bit in excess of 200 billion. Now, if you look at the average wealth in the United States per person, it's around $500,000, $500,000. And median wealth is just $85,000. So median wealth and and average wealth are very different by a factor of about 5. That's because we have a highly unequal distribution. Now, if you compare Elon Musk 200 billions plus to average wealth, which is around more or less $500,000, you find, okay, if you take an average 400,000 people in the United States, they have as much wealth as Elon Musk. Well, and in our model, we do not get to this number. So in our model, the richest person, well, he has about 10 times average wealth in the model, not about 400,000 times. So you need an additional model to have people like Elon Musk, Bill Gates, and people in this very rich percentile in the model. Okay, so let me get to the cyclical results here, to the cyclical properties of the income distribution in the United States. And you find that the bottom 3 quintiles of the income distribution, the first 20%, the next 20%, and the third income quintile, they are positively correlated with output, around 0.3 to 0.5. The next 2 quintiles are negatively correlated with output, while the top 5% of the income earners, their income share is non-cyclical. Now, Castaneda, Rios-Roll, they used infinitely lived agents in their model, and they are able to replicate that the first 3 quintiles are positively correlated, so pro-cyclical income distribution for the lower income shares, anti-cyclical income shares, upper income shares. But as you can see, of course, they cannot replicate the top percentiles here, the top 5% accurately. And the first 3 income share quintiles here, the correlation with outcome is too close to 1. So they, as a mechanism, they introduce unemployment. Unemployment is strongly anti-cyclical. So in a boom, people find a job, especially the many low-income people find a job, and this raises their relative income so that the income share is highly pro-cyclical. But it comes at the cost that it's too pro-cyclical, while the top income shares are too anti-cyclical. Now, we look at a model with finite lifetime, and in this model, one mechanism is that we have retirees, which cannot change their income by much. They do not work anymore, by definition. So this, of course, has an effect on all kinds of income shares, because we have rich retirees with a high capital income, high interest earnings, high pensions, and we have low income retirees who have only a low income, low pension, little wealth, and receive little interest income on their wealth. So we have pensions in every income quintile. So that reduces the strong pro-cyclical behavior of the lower income quintiles. As you can see, the number goes down, the correlation, and also reduces the strong negative correlation of the top income quintiles. So this helps to get a little closer to the empirical values with respect to the first 4 income quintiles, but not in the top income quintile. And we also analyze whether it makes a difference whether the pension is progressive or not. So let me explain what I mean by progressive pensions. A progressive pension is a pension that redistributes among retirees a lot. So some people pay a lot of contributions and usually get a higher pensions, but in a progressive pension system like in the United States, this is redistributed among the retirees to a large extent. And we distinguish these 2 cases where pensions, on the one hand, are proportional to the productivity types, to their income, and one that is a lump sum pension, which is our case 2, And as you can see, well, both have their advantages and disadvantages. So for example, here we find that for the lump sum pensions, a progressive, very progressive pension system, we are not able to model the behavior of the second income quintile, while we do much better in modeling the top income quintile. Well, you weigh these trade-offs. So our preferred model is probably the one here, model one, where we have a more proportional pension system, where pensions increase with contributions. So a topic for your PhD thesis, if you're still looking for a paper, well, try to replicate these income shares, their cyclical behavior, and try to match them to the empirical shares. You may use a combination of the model by Castaneda and our overlapping generations model, so meaning that you introduce unemployment into our overlapping generations model. And you may also add some elements that improve the lead-lag structure in our correlates here, in our second moments. For example, sticky wages and demand shocks, which may help to explain business cycle dynamics to a larger extent. So this would be a topic for PhD. See this, combine overlapping generations model elements with the elements of unemployment, add something like a demand shock, sticky wages, and try to replicate the cyclical behavior of the income shares. Well, one important step here in our algorithm, we just look at two possible technology values here. So we identify high technology with a boom and low technology with a recession. And we have a lot of jump behavior up and down. So let me show you how a typical time series in our model, this is a simulated time series, looks like. At period 60, for example, we have high productivity, we have a boom. And in period 65, high productivity jumps down to low productivity, and so does output. Now, if you also, this is typical element of the Krusell-Smith algorithm, you might want to introduce more values for the discrete values, more points on the distribution of the technology level Z, so that production does not jump up and down, and get to a better description of the empirical cyclical behavior of the distribution. Let me point out one problematic point, and to the best of my knowledge, nobody has really explained this well in the literature yet. So we do have a problem when we look at historical episodes. They do not behave all alike. So if you look at these statistics here by Rios, Rull, Castaneda on the empirical correlations of the income shares, this is an average over a long time horizon, couple of decades. Now this suggests that income shares always behave like this over a typical cycle here. Now this is not the case, so let's look at capital income, which is very problematic, very sensitive to the episodes that you study. So for example, during the Great Recession, 2007 through 2009, the origin of the crisis was in the housing market, in the financial markets, the subprime crisis. As a consequence, returns on stocks, as for example measured by the Standard & Poor's index, Standard & Poor's 500 index, well, they were significantly negative, minus 38%. That's the fall in Standard & Poor's 500 index. So capital income during this period, if you were holding stocks, you had a loss. Now contrast this with the most recent crisis, the COVID-19 crisis. And if you study the year 2019, so over the year 2019, the Standard & Poor's 500 index, well, it increased by 28%. So just the opposite behavior. Here the problem was an epidemic which inflicted both supply and demand shocks in our model, but it did not originate in the financial markets. And here we find that, well, rich people got richer during the COVID-19 crisis, and we have an increase in inequality and high returns from stocks. And to model these special particular characteristics of the episodes of different recessions is a challenge. And if you combine this with the points I have mentioned before, a combination of unemployment with finite lifetime, demand shock, sticky wages, and a better approximation of the technology shocks, well, you really might have a nice PhD paper and a nice idea for an article. Let me emphasize right now a crucial point in your consideration of a paper project, of your PhD thesis, of a research topic. What shall you pick? Well, these heterogeneous agent models, especially with idiosyncratic uncertainty, are quite hard to compute. So it's a big investment. You have to learn the code, you have to know where to adjust the code, you need to know how to program code, a couple of hundred lines of computer code. And this is, of course, an investment which will take you a couple of months. Well, that's a long time for your PhD thesis. But let's look at the alternative. In the first part of our book, we consider representative agent models, and the majority of representative agent models are, you can compute them with the help of a software package. Let's say our Quorum package that we provide for our book in MATLAB and in Gauss, and you can just simply apply it and just have to compute the equilibrium conditions in the model. Let's say 20 or 30 equilibrium conditions, which are characterizing the general equilibrium, the steady state, and the dynamics in your model. And the rest is done by the computer code. Now, of course, this is really tempting. On the other hand, if you look at our problems here, heterogeneous agent models with uncertainty, idiosyncratic, and aggregate, well, to program, let's say 500, 600, perhaps 1,000 lines of code is very difficult. But you also need to consider the risk that your strategy to use a representative agent model is implying. So there are a couple of hundred per 1,000 PhD students who use representative agent models. They combine different elements, different papers, different models, and put them together in one big model. I can remember one PhD course that I gave at Luxembourg, and one PhD candidate came to me and asked me, well, here I have this model which combines the models of X, Y, and Z, 45 equations. Here is a computation with Dyna. What can I do with it? And that's of course the problem, that the competition is very hard in these papers, where you do not have to use sophisticated methods, idiosyncratic methods, which you have to program yourself, but use a package that is available to many students with a minimum of effort to get into. So we have some kind of some kind of competition in economics and macroeconomics, for example, which is the best monetary policy model. So we have the model by Cristiano, Eigenbaum and Evans, or Smith-Walters, and they are applied for monetary policy analysis by the central banks. And the beauty of our profession is that, well, every year or every other year or something big happens, like the Great Recession 2009 or the COVID-19 crisis. And these kind of events give us an impetus to develop new models. So for example, the Great Recession resulted in an interest into the housing crisis. So if we integrated housing models, perhaps partial equilibrium housing models, into our general equilibrium to compute it. In the 2019 COVID-19 crisis, we observed, well, we have an epidemic. It affects both supply and demand. So we have little, smaller supply of labor, and we have, for example, a drop in demand in the service industry. We do not go out for lunch anymore or for dinner. So how do we model this? Well, we have to introduce something like a two-sector model, one where labor is used in contact with people, and perhaps another sector which can rely more on home office work. And with consider supply and demand shocks in such an environment. And there, of course, is a development, a dynamics that we keep on developing these kind of models. But there are a couple of hundreds of thousands of people who try to do this. So if I have to take a look at my profession, go, let's say, to a conference of the Society for Economic Dynamics or Computations in Economics and Finance, and consider and study the program, well, every second macroeconomist now is working on such kind of model to consider the COVID-19 crisis and the DGE models, and combines difference or introduces new elements in the standard general equilibrium model. Now, in fact, why not use an artificial intelligence unit, program it so that it combines all available dynamic general equilibrium, partial equilibrium models, and combines the equilibrium conditions, puts it in the package like DYNA or Quorum, and just computes and studies which one is fitting our data the best. And this is not possible, at least with current technology, for our heterogeneous agent models. So if you study an overlapping generations model with heterogeneity, within cohort heterogeneity, and have to program it, you have to do it find an individual solution for each problem, and therefore you can be safe. Well, overnight there's no one else who does exactly the same problem. So that's kind of a relief for a PhD student, I guess, to find out, well, that perhaps 50 or 100 PhD students from MIT, which work on macroeconomics, and half of them use a package like Quorum or DYNA. Well, he will not be the first one to find the results and drive you out of the market with his paper. So my recommendation is, well, yes, it's much harder to get into these models, program them, but it's more rewarding. The competition is less because people do not invest that much time into computational methods. So, and one key in the computation of heterogeneous agent models is runtime, computational time. So let us look at our results here. We provide the code in Python and in Gauss. And there are a couple of fragments of steps in this program. And let me comment on the computational time for these steps. So in the first part, we have to compute the non-stochastic steady state. So where we, for example, set the technology level, which fluctuates to its mean value, and study what's the allocation in this economy. That's a non-stochastic steady state, and with Python we need 11 minutes to compute it. With Gauss we need 2 minutes. And that's a general observation from our side here. When we look at standard programs like MATLAB and Python on the one hand, they are much slower than, let's say, Gauss or Julia. And these are a little slower, but not much slower than Fortran and C++. So the advantage that you gain from going from Gauss or Julia to Fortran and C++ is small, because the time that you save in computational time and runtime, well, it's usually you have to invest more in programming time, because these programs codes are more sophisticated, more cumbersome, and so we recommend to use something like Gauss or Julia for these kind of problems. Well, Python and Julia have the advantage that they are freeware, so you can download them and you don't have to pay anything for it. And they have huge libraries which are also available. Python is a little easier to get in than Julia, admittedly. Okay, and we find that MATLAB is also very slow compared to Gauss, Julia, or C++ or Fortran. But it has the advantage that it's, of course, has a lot of libraries and code that is available online. But it's expensive, and it's so if you look at the dynamics in programming code, Python is probably the code with most applications and the biggest dynamics. So it's a hard choice you have to take. But if you, for example, look at the total runtime here in Python, it took us almost 2 days to compute this particular application that I will present to you next, while it only took 5 hours in Gauss. And if you use something like Fortran or C++, you will get it down to 1 or 2 hours. Second big part in this model is to compute the policy function. And the policy functions, so optimal consumption, optimal savings, optimal labor supply, depend on individual characteristics, which is your own wealth, your individual productivity, and your age. That's the new dimension in this model. Individual age is the idiosyncratic variable state here in this model, and the aggregate variables, which is aggregate technology and aggregate capital. So that's why it takes so much time to compute policy function, 39 minutes with Python and 14 minutes with Gauss, because we have, in fact, we will have 6 variables in our policy and value functions. And this, of course, if you, for example, we choose something like 50 grid points for wealth, for individual wealth, and something like 8 grid points for aggregate wealth. So, and we have something like 70 different ages. So you can imagine we have to compute policy and value functions at many, many grid points. And this is what slows down our program. Now, the biggest factor with Python, however, is the simulation. So we simulate the economy using a realization of 200 periods, 200 shocks in this economy. And this is so time consuming in Python, more than 1 hour, while just take 3 minutes in Gauss. And this is really the factor that is slowing down our computation. And I will point out in the third part of this talk why Python is so slow in this particular problem. Now you can download this code here from our homepage. So this is the homepage here of Dynamic General Equilibrium Modeling, Computational Methods and Applications. You find the address, of course, up here. But you can just Google it by typing Herr Mausner Dynamic General Equilibrium Modeling, and the first entry here is already our download page for our book on dynamic general equilibrium modeling. And when you scroll down this page here, you find, for example, the quorum package for the computation of the representative agent model, where you just have to provide equilibrium conditions in MATLAB and in Gauss. And we provide lots of other code in Gauss, Python, Julia, and Fortran. So here for our second edition, you find the code for the application that I will present to you next. Here, chapter 10, just download the zip file for either Gauss or for Python. We also provide Fortran and Julia code for many other applications in this book. And you will also find the slides, the description, a manuscript where I lay out in detail of what's done in this particular application. In fact, you don't even need to buy the book. So the manuscript provided here on this download page should provide you with enough material to study the particular application Krusell-Smith algorithm in the overlapping generations model. Let us get to the second part of this presentation, the overlapping generations model. I will describe to you in the following the model that we're using, a 70-period overlapping generations model. And finally, in part 3, I will finish with the description of the computational details, the Krusell-Smith algorithm. I will first present the demographics of our model before I get into the household behavior, describe the optimal intertemporal utility maximization, and then continue to look at the production sector and the government sector. So we have 70 cohorts in our model. Agents live from period 21 till age 90, which correspond in our model to periods 1 through 70. Each year, a new generation is born at age s equal to 1, and the survival from age s to age s plus 1 is stochastic. So we denote this survival probability with phi st, so the probability of surviving from period t to t plus 1, from age s to s plus 1 is described by phi st. Now, since we will study a stationary equilibrium and look at the dynamics around the stationary equilibrium, we will use the same survival probabilities phi s in every period t. The first 45 years, households are workers, and the final 25 years, there are retirees, and labor supply falls to 0 in old age. The survival probabilities are taken from the United Nations. So here we have the survival probabilities in the year 2015 in the US as estimated by the United Nations. And as you can see, of course, the young people, they survive basically with probability 1. And if you get up to age 90, survival probabilities go down to something like 90%. And in the final period of the life, age 90, well, their survival probability will go down to 0. They will not become 91 in our model. You can extend your model if you like and look at longer lifetime horizons, longer longevity. Please feel free to adapt our code. The variable NTS describes the number of households at age S in period T, and NT is total population. And we assume that total population grows at the rate Gn, and that the newborn cohort at age 1, well, they grow at the rate n. And in the stationary equilibrium with constant population growth rates and constant survival probabilities, the newborn growth rate nt is equal to the population growth rate gnt. This is not the case during the transition. For example, now in the demographic transition, this is holds only in stationary equilibrium. And we set the population growth rate to the empirical value, which is 0.75 in the last decade. The households, they maximize intertemporal utility, and they discount utility, expected utility by instantaneous utility in every period by the factor beta. Now, they only survive with a probability phi to enjoy utility from consumption C and leisure 1 minus L. Now, we also have the expectation operator here, ET, because households' productivity and hence income, consumption, and labor is stochastic. Now notice that the effective discount rate here is beta times phi times the survival probability. So that's why we will calibrate phi higher in this overlapping generation model than you're used to from the Ramsey model. So we will set beta equal to 1.011 as estimated by Hurd, who explicitly accounts for stochastic survival. So if you, for example, take the product of beta times phi, how the discount factor falls below 1 in mid-age of your lifetime. Instantaneous utility is chosen to be a Cobb-Douglas function, so in the two goods, consumption and leisure. And gamma here is the weight of consumption in utility. We calibrate gamma here so that we have an average labor supply of 0.3 in our model, so 30% of available time. That's the working time of the working agents. Now with this kind of utility, with this Cobb-Douglas utility, we can only fix one variable in our model, which is the average labor supply. We cannot fix, for example, the Frisch labor supply elasticity, so how labor supply reacts to a change in wages. And the implied Frisch labor supply elasticity for our calibration gamma equals to 0.29. Who has an average labor supply of 0.3, well, his labor supply elasticity amounts to 1.5 in our model. So it's a little bit higher than usually assumed in macroeconomic models, where you choose something like perhaps 1.0, like for example, Trabant and Ulich in their model. But it's in the range of what's observed for macroeconomic labor supply elasticities. Notice that it's much higher than in partial equilibrium. So for example, we consider that we have adjustment along both the intensive and extensive margin. So meaning that we decide whether we should work at all, and if we work, how many hours we work. So that's why the macroeconomic elasticities are usually larger than the microeconomic elasticities are used in microeconomic quantitative studies. And we set an intertemporal elasticity of substitution here equal to 1/2, corresponding to a value of eta equals to 2. The working household receives net labor income 1 minus tau L minus tau P times epsilon times A times WL. Now, A is our aggregate labor productivity, which grows at an exogenous rate GA, which we will calibrate to equal 2% annually. And our individual productivity here, epsilon, is affected by HS, a permanent productivity type E, and idiosyncratic component theta. S is H, and the idiosyncratic productivity epsilon, we choose a product of the permanent productivity E, stochastic productivity theta, and the H component. The H component, well, we take the profile estimated by Hansen in 1993, but it hasn't changed that much. It's presented here in this figure. As you can see, for example, the 50-year-olds, they have maximum, 51-year, 52-year-olds have the maximum H productivity, which is about twice as high as the H productivity of the 21-year-old. And we copy this H profile. Now, this is an important aspect of overlapping generations models. So with the typical neoclassical growth model, the Ramsey model, even if you have heterogeneous agents, you do not capture this H productivity profile. And this, of course, you loses lots of information and perhaps important characteristics of your economy. Just look at the United States, which is now in the demographic transition. So the number of young people, age 20 to 30, falls relative to the people around age 50. So we have an age composition effect of the labor force with more productive workers in the upcoming years. And this is not captured by standard Ramsey type models. And this might also have an important effect on distribution. So, for example, we have aging in the United States, we have more productive agents. This should decrease inequality in the labor distribution. So just assume the extreme case that today we have just one guy who's 52 years old with maximum age productivity, and all others are 20 years old. Then we have, of course, much higher inequality, income inequality, than if we, for example, had, 50% young people and 50% people around this age here. So we expect that income distribution is becoming more equal because of the age composition effect. And to neglect this, of course, can have significant quantitative effects. That's why we like overlapping generations models that much. It can deal with the demographic transition. The second component here is the permanent productivity type, and it reflects that we have high school students and college graduates in our workforce, in our labor force. And we calibrate epsilon so that it reflects the average skill premium, the wage premium of college graduates vis-a-vis high school graduates. And in the United States, according to current data and current estimates by myself, is around 150%. And this is reflected in exactly choosing the two states, 0.57 or 1.43 for the permanent productivities. So we normalize it to 1, these two values here, and the premium is 150%. So if you multiply 0.57 times 2.5, you get to 1.43. And we take the estimates for the stochastic component from the paper by Sturz, Lenton, Telmer, and Yaron, 2007. And they calibrate a two-state Markov process for this idiosyncratic stochastic productivity theta with the values 0.727 and 1.233, again, with a mean of 1. And it's, as you can see, it's highly autoregressive. So the transition matrix pi to get from state theta to next period theta prime is highly persistent with 0.98, and only with a probability of 2% you change your idiosyncratic productivity component type. So this is in accordance with empirical observation on the conditional variance of individual income, individual earnings. The individual income is taxed at the rate tau L, the wage tax, and tau P, which is social security contribution, and we assume proportional income taxation here, labor income taxation. So this is, of course, a simplification. You're invited to introduce progressive income taxation as you find in the United States. And with the definition of net labor earnings, we can derive the budget constraint of the worker at HS in period T, which is given by his labor income. He will also receive transfers from the government, lump sum transfers. He earns interest income RT on his wealth KST, and he has to pay capital income taxes tau K on his interest earnings R times K. He spends it on consumption C and pays consumption tax tau C, and on next period wealth KS plus 1 in period T plus 1. The retiree receives a productivity-dependent pensions pen of E in period T, which does not depend on his age, but only on his permanent productivity type. Well, of course, this is a simplification. We do not introduce contribution-based pensions, so people who contribute a higher share of the higher contributions to the pension system, social security system in the United States, they also get a higher pension. We only model this by considering that the fact that higher permanent productivity households also get a higher pension here. In chapter 10.1 in the book, we introduce contribution-based pensions, where we explicitly account for the pension schedule and the contributions in the United States. And receives transfers as well. The taxation of consumption and of interest income, of course, is the same as in the case of the worker. And at age S equal to 71, corresponding to age 91, in real life, the household is dead. And of course, at this time, since we have no bequest motive, his wealth is equal to 0. And the labor supply, of course, of the retiree is also equal to 0. In addition, we impose a credit constraint, so household cannot borrow. The production sector is characterized by perfectly competitive firms, both in the goods and the factor markets, so that factor prices are equal to the marginal products of labor and capital, respectively. Production is a Cobb-Douglas production function in capital K, aggregate capital, and aggregate labor times aggregate labor productivity, ATLT. It's Cobb-Douglas, where we choose the production elasticity alpha equal to 0.35 in accordance with empirical estimates for the United States. And we have the stochastic technology here, stochastic productivity ZT, which follows a two-state Markov process. So this is taken from the original article by Krusell-Smith in 1998 in the Journal of Political Economy. And we calibrated as Krusell-Smith with a two-state Markov process with values Z1 and Z2 equal to 0.98 and 1.02. And this will imply a standard deviation of annual output of about 2%, as you observe in the United States. And the average duration of the cycle is calibrated to amount to 6 years, which provides us with transition probabilities of 2/3 and 1/3. So with a probability of 2/3, we remain at the previous productivity Z. Now, the firms maximize profits, which are given by production minus labor cost, wage cost minus interest rate cost minus depreciation, so that we get that the WT, the wage rate, is equal to the marginal product of labor, and the interest rate, the real interest rate RT, is equal to the marginal product of capital minus depreciation delta. Finally, we have the government sector. The government sector is described by equation 10, so the fiscal budget is balanced. Expenditures amount to transfers plus government consumption, and we will set government consumption to 18% of steady state output, so non-stochastic steady state output, so that government consumption in our model is constant. And government consumption is financed by labor income taxes, capital income taxes, consumption taxes, and the government also collects accidental bequests. So let's take a look at, for a typical household, let's say aged 80 in real life, which corresponds to period 60 in the model, and with a certain probability of around 7–8% it will die. So we need to take care of what's happening to these accidental bequests. And we assume that the government collects it and distributes it to all households. There are different ways you can handle accidental bequest. One is that you introduce, that you redistribute the bequests, for example, among those agents who are 25 or 30 years younger, typically those who inherit the bequest of this cohort. You can introduce a parent-child link, which makes it even more difficult, because you also have to use the wealth of the parent as an additional idiosyncratic state in the individual state variable. Or you could, for example, introduce annuity markets, so that the household signs a contract with a financial intermediary who just takes the savings and distributes the accidental bequest for the savings of those who do not survive to those in the cohorts who will survive. So you'll find these different applications in our book. Accidental bequests are not a large percentage here in total wealth, so it's not really that important in our model here how you handle the bequest. Now, as you can see, during the economic cycle, for example, in a boom, wages, interest rates increase, consumption increases, so taxes will increase. What's happening? Well, the fiscal budget adjusts, then also aggregate transfers, which are equal to individual transfers times population size, will increase in this case. And the second government authority here is Social Security, and the Social Security budget is assumed to balance. So total contributions, tau P times total labor income, AT-LT, WT, is used to finance aggregate pensions, PEN-T. And we consider two types of pension, as already mentioned. First case is a lump sum pension. Second case is the pension that depends on the permanent productivity type. In the first case, the individual pension, lowercase PEN-T, is equal to average net wages. So where the idiosyncratic productivity is equal to 1, and the labor supply, L, is equal to the average labor supply. Well, and Ripple describes the net replacement rate of pensions with respect to wages. So notice that in this case, of course, our pensions fluctuate over the business cycle in the same way the wage rate fluctuates, but it does not reflect the movement of the labor supply. So average labor supply, for example, is higher in the boom than during a recession. And we do this basically for computational convenience so that we do not have to introduce average labor supply as an aggregate state variable here in our model. In the second case, where pensions depend on the permanent productivity type to reflect the observation that college graduates earn higher pensions in old age than high school graduates, we also multiply individual pensions here by the permanent productivity E of the aged. Now, to transform variables into stationary variables, we divide individual variables by aggregate productivity, labor productivity A, except for the labor supply, which is already a stationary variable. And for the aggregates, we divide it by the product AT-NT, aggregate labor productivity A times population size N, with the exception of aggregate labor supply, which we only divide by the total population NT. And in this case, aggregate transfers, uppercase TRT, are equal to individual transfers, lowercase TRT. Now we can define an equilibrium, and I will skip through this quite quickly because we have described basically all the equilibrium conditions already. So population grows at a constant rate n. The size of the different cohort is given by NTS, and the shares of a cohort at HS is constant, which is equal to NT over S over NT. Firms maximize profits so that factor prices are equal to the marginal products. Households maximize their lifetime utility, and the policy function that results from this utility maximization are next period wealth K prime, consumption C, and labor L. And they depend on the state variable Z, and Z is composed of 6 variables of HS, permanent productivity E, idiosyncratic component theta, individual wealth K, aggregate technology Z, and aggregate capital stock K. Now we compute the policy function over a grid of functions. So we have 70 70 cohorts with 2 permanent productivities and 2 idiosyncratic productivities. The capital stock, we will choose a grid of 50 points where we compute the policy function. Aggregate technology Z has 2 states, and aggregate capital stock, we discretized the distribution at 8 points. So this leaves us altogether that we have to compute the policy function for 224,000 points. And of course, this is what makes this algorithm really slow, because we have to compute it a lot of times, not only once, but a lot of times. We have a distribution function in period t of the individual variables s, e, theta, and k, which is described by f, and we will compute it. We again will use a discrete approximation, so we approximate the individual values k at 50 grid points. Aggregate values are the sum of the individual variables, which are our consistency conditions. So for example, aggregate labor supply is equal to the labor supply of the workers. So from HS equal to 1 to HTW equals to 45 over the 2 stochastic productivities, theta 1 and 2, over the permanent productivities E1 and E2, and over the 50 wealth grid points over the interval K. And then the aggregate productivity is equal to the product of the efficiency epsilon times labor supply L times the distribution F times the measure. And we just sum it up over all working agents and their measures F. The fiscal budget is balanced, and we assume that capital government consumption is constant over the cycle. And again, we can, for example, derive aggregate consumption with the help of the consistency condition that it's equal to the sum of individual consumption. We can derive an expression for accidental bequest, which is given by the first equation on this slide here, and is derived in the book. And we have that the goods market is clear, so total production Y is equal to total consumption C plus government consumption G plus investment, and investment is given by the capital accumulation KT plus 1 minus KT and minus depreciation delta times KT. And to close the description of the equilibrium, well, we need to describe the dynamics of the distribution function, which will take place in the next part of this talk when we look at the computation of the dynamics with the help of the Krusell-Smith algorithm. So let me go through the calibration quickly before I get to the final part of this talk, to the Krusell-Smith algorithm. We choose a production elasticity of capital equal to 0.35 and a depreciation rate of 8.3. These values are taken from Trabant and Uhlich. The growth rate of output in the United States is approximately 2% over the last couple of decades, and the intertemporal elasticity of substitution, like most often in our book, we set equal to 1/2. The preference parameter gamma, which determines the weight of consumption in utilities, set equal to 0.29, so that average labor supply is equal to 0.3, and the discount factor beta is set to 1.011, in excess of 1 because we also have stochastic survival in our model. Population growth rate is equal to 0.754%. The labor and social security tax, the sum is equal to 28%. The capital income tax rate is equal to 36%, so these are estimates by Mendoza. Consumption tax is 5%. Our government share is equal to 18%. And the net pension replacement rate, this is a number that we take from the OECD, is close to 50% in the United States. So this describes our model and its calibration. In parts 1 and 2, I've presented to you the model and the result for the cyclical behavior of the income distribution. Now in part 3, computation of the dynamics Krusell-Smith algorithm, I will show you how to compute this model, how to compute the dynamics, explain to you the Krusell-Smith algorithm, and of course this is the main part of this presentation and of chapter 10.2 in our book. The algorithm follows Krusell and Smith, the JPE paper 1998, closely. So in the first step, we compute the non-stochastic steady state with a constant aggregate technology z equal to 1. And we will store the policy function and the steady state distribution for later use. In the next step, we have to choose parameterized functional forms for the law of motion for the aggregate next period capital stock, and present period employment and present period transfers. So we need these because the household has to forecast the factor prices and his pension in the next period so that he can determine his optimal policy function, its labor supply today, and his savings in the next period. And we will copy the functional forms for the dynamic equation 15a from Krusell and Smith, and the equation 15b and 15c are new because these are missing in the model of Krusell and Smith. In this third step, we solve the consumer's optimization problem now as a function of the individual and the aggregate state variables. So we also consider the aggregate technology Z and aggregate capital stock K as states in our policy function here. In the fourth step, we simulate the distribution of the dynamics of the distribution functions relying on these policy functions. So we have a particular productivity Z in this period. We know the probability that it takes Z prime in the next period. So we use a random number generator to determine which will be the value next period. And for this new value, Z prime, and for the capital stock K prime, we can compute the dynamics of the distribution function. We simulate the model. From the simulation, we get a time parse for the distribution. And of course, if we determine the aggregates from the distribution, we get a law of motion for K, L, and transfers for our aggregate state variables. And we use these time paths to update our functional relations 15a, b, and c by updating our estimates for these functional relationships until they converge. And we test in the final step, step 7, we test the goodness of fit for this function using, for example, R square, and we will find it's close to 1. And if it's satisfactory, we stop. Otherwise, we have to re-specify these functions g in step 2 and go back to step 2. Okay, now let me get into the individual steps here. And in particular, step 1, the computation of the non-stochastic steady state. Step 3, the solution of the consumer's optimal policy function. And step 4, the dynamics of the distribution, the simulation of the dynamics are the time-consuming and difficult parts. Now let me start with step 1 with the computation of the non-stochastic steady state. We have two loops, two nested loops. In the inner loop, we compute the individual policy function for given exogenous aggregate variables, K, L, transfers, and pensions. And in the outer loop, we update the aggregate variables. So let's look at the inner loop first. Let's assume we have an aggregate capital stock K in the non-stochastic steady state, aggregate labor L, aggregate transfers TR, and pensions PN in the non-stochastic steady state with constant aggregate technology Z equal to 1. Now there are basically two options how we can compute the individual policy functions. The first one we have used over and over in the preceding two chapters, which is value function iteration infinite time. This amounts to using numerical optimization methods. Now these methods we find are too time consuming here for this large scale application, and we use the Euler equations approach instead. So we can express the first order conditions of the household with respect to next period consumption, this period consumption C and next period wealth K prime, the Euler equation, and the second equation, which is the first order condition with respect to labor, in which we substitute the budget constraint. So these are two nonlinear equations, and we use a nonlinear equation solver to solve this for all grid points of the individual state space, for all 228,000 grid points. As with value function, we start in the last period of life, so at age s equal to 70, corresponding to the empirical age of 90, the last period in our life here. And we know that next period we are dead, so we do not save, so that K prime is equal to 0 for all grid points S, E, theta, and K. HS, which is equal to 70, permanent productivity E, idiosyncratic productivity theta, and individual wealth K. Now we iterate backwards over age, starting with the 69-year-old, 68-year-old, and so on, and go back to H1. Now let's take a look here at equation 16a and 16b, which are the optimal policy optimality condition, the Euler condition, and the optimal labor supply for a worker. The case for the retiree is much simpler because labor supply is equal to 0, so equation 16a drops from this equation. We can express the Euler equation as a residual function, and for which we look for the root, for the solution that RF is equal to 0. So in this Euler equation we have present marginal utility from consumption is equal to discounted expected marginal utility from consumption in the next period times 1 plus the net interest rate. So this is the most familiar, I hope most familiar Euler equation here. We discount by the factor beta and the survival probability phi, and we have the expectations operator because individual idiosyncratic productivity theta is stochastic. So we know the transition probability from our calibration exercise. Now the first order condition with respect to labor, and I encourage you to derive this, is expressed as equation 16. For our Cobb-Douglas case, this is a nice and easy equation, so we can solve for the optimal labor supply in equation 16a. And the consumption follows from the budget constraint 16b. Now it may happen that in equation 16a, the optimal labor supply is below 0, so that you would get like to get more than 100% of your available time of one in the form of leisure, and we restrict our labor supply to be larger equal 0, so we cannot buy extra time in our life to enjoy leisure. And we solve this equation for each grid point of the individual asset space with the help of a nonlinear equation solver. This is, in our experience, much faster than value function iteration. Now, there are 2 points which I would like to draw your attention to. The first one is we might have a corner solution. So for some household, it may be optimal to rather accumulate debt and consume more so that K prime, the next period savings, are negative next period wealth. Since we assume a credit constraint, K larger equals 0, and therefore also K prime larger equals 0, we need to test this, and whenever the residual function is larger than 0 for K prime equal to 0, we know that we have a corner solution. In this case, if K prime is equal to 0, we would like to have a higher marginal utility of consumption in this period by increasing our consumption and decreasing next period wealth, incur debt, and therefore have lower next period consumption C, so that marginal utility next period goes up. Okay, this is the first thing we have to check, and if this is the case, we know, okay, optimal next period wealth is equal to 0. Once we have settled this problem, we need to solve the nonlinear equation system and provide an initial guess for the next period capital stock. And for the particular state at HS with permanent productivity E, idiosyncratic productivity theta, and at the grid point KIK. Now, this is a tricky issue, and this is crucial. Let me emphasize this. We will propose 5 different guesses, and we take the one which is closest to the solution so that its absolute value is closest to 0. And this is the one we will finally pick and supply it to our nonlinear equation solver, which might be, for example, in our case, a modified Newton-Raphson method. So we look at these values. We look at the case at the grid point just one point below our present grid point KIK. So we look at KIK minus 1 and see what's the solution and test, well, what is the residual value for KIK 1 minus 1 here in this equation. Next, we look at the household who is 1 year older. Remember that we move backwards in time, so we already have the solution at HS plus 1 when we consider the agent now at HS. We can look at the case, what's the residual function, the value of the residual function, if we just keep constant wealth, if we use 0 wealth, so consume all our wealth. And we also checked, well, we computed something like a maximum possible value for next period wealth by assuming that we have a very small consumption, C equals to 0.1001, and supply maximum labor supply. In our case, we set it to 0.7, and then just use half of this value for next period capital stock. So we test these 5 options and pick the one which has the lowest absolute value for the residual function RF for our Euler equation. And in this case, we get lucky, we always find a solution. I've played around with many different specifications, so just use 1 or 2 or just 3 or 4 or something like this. And in this case, the total algorithm may come to the total computation may come to a halt because the modified Newton-Raphson method does not find a solution. The initial value is not close enough, and you know this from our book and from other books on numerical methods, that you need to supply a good initial value in the case of Newton-Raphson algorithm. Otherwise it may not converge. So that's a tricky issue, and you need to be aware of this fact. And that's why, for example, problems like these are difficult to program. There is no standard way like in our quorum procedure or in Diner. You need to adjust your code. You need to understand the code. You need to understand where there might be a bug or where it might come to a halt, and adjust your computer code at this particular line, at this particular computational line here. A third problem that I need to mention here, the next period capital stock K prime may not be a grid point, so it may be hard to compute to find optimal next period consumption for next period wealth k prime, which is not a grid point because we have not stored this policy at this particular point. So we just have stored it perhaps at neighboring points. And what we do in this case is we use linear interpolation here of the policy functions C prime, L prime at the next period wealth K prime. You may resort to other interpolation like cubic spline interpolation or so on. We just chose the easiest one so that for you, if you want to check our Python code or our Gauss code, it's very easy to follow it. So we just always use the simplest solution here. Now we have to choose the S-limit grid for the individual wells. We choose 0 and 10 with 50 grid points. And we have to check if our upper capital stock k equal to 10 is non-binding, and this is the case. So here you find the distribution of wealth in our steady state, and we have almost 75% of households who are credit constrained here, have zero wealth, and the maximum wealth is equal to 8.2. Average wealth is about 1.8. So this is already what I pointed out to you, that our richest household here with wealth of equal to 8.5 approximately only has something like 5 times average wealth, which is equal to 1.8. So we do not have Elon Musk in our non-stochastic steady state distribution of individual wealth K. In the outer loop, we have to update our aggregate capital and aggregate variables K and L. So we first have to provide an initial guess. We start by assuming that the labor supply, average labor supply, is 30% of our available time, which is equal to 1. Our labor force is approximately 2/3. So 2/3 of our population are workers, 1/3 are retirees, and our population is normalized, the measure is normalized to 1. So we multiply 0.3 by the measure of 2/3, assuming here that everyone works 0.3 in our economy. So this provides us with an aggregate labor of 0.2. And choosing an initial interest rate of 2%, we can use the first order condition of the firm with respect to capital, which sets the real interest rate R equal to the marginal product of capital minus depreciation. And from this equation, we can derive capital stock because all the other variables are known. Now, when we have computed in the outer loop a first guess for KL transfers and pensions, we said transfers equal to 0 and pensions follow from the wage times the replacement rate. We compute the individual policy functions, and with the help of the individual policy functions, we just sum up the individual policies to get new aggregates, and we update the old aggregates in the former loop, in the former iteration, by 30%. Now the computation here takes 2 minutes with Gauss, and with Python it takes 12 minutes. So it's really fast. So the steady state computation with the help of Euler equation approach rather than the value function iteration approach is very fast. Step 2, we have to choose an initial parameterized functional form for the law of motion for aggregate next period capital stock K prime and present period employment and transfers L and transfers. So we choose the functional form for the capital next period capital stock Kt plus T plus 1. That's chosen by Krusell-Smith. So we choose a log-log specification so that the log of aggregate capital stock next period is a linear function of the log in this period of capital stock in this period. And we also account for the technology aggregate state in the present period, if it's equal to Z1 equal to the recession equal to 0.98, then we add omega k2 to this equation, and here we have the product of the index function 1 of zt equal to z1, which is equal to 1 if zt technology is equal to the z1 to 0.98 in the bad state, times the logarithm of the capital stock. And the households, they observe the capital stock and the technology level, and we find a law here for the aggregate capital stock that it's a function of the aggregate labor, which is a function of aggregate capital stock and aggregate technology in the same period, because households decides upon the labor supply after they observe the beginning of period capital stock K and the technology level ZT in period T. And this, we also choose a log specification. And with regard to aggregate transfers, we do not choose logs because transfers are maybe negative or close to zero. So in this case, a logarithmic function is not warranted here. As initial values, as initial guesses for omega, we simply calibrate them so that we expect next period capital stock to be equal to the steady state capital stock, and similarly for labor and transfers. So this provides us with an easy initialization of these parameters. The solution here is presented by omega k, omega l, and omega transfers. And as you can see here, we have the autoregressive component 0.9257 of the capital stock. So the log of capital stock next period is 0.9257 times the log of the capital stock this period. We have a stable relationship here. So the autoregressive parameter here is 0.92. It's smaller than 1. And this looks like a reasonable solution. Now we get to these coefficients by regressing kt plus 1 or log kt plus 1 on log kt and our index function here. And we find that our regressions yield a very high R squared. It's basically indiscernible from 1.0. So we can be quite confident here that our parameterization, our choice of this functional form here, as shown on the top of slide 44, is a reasonable one. Step 3. Now we solve the consumer's optimization problem as the function of the individual and aggregate state variables. So we want to compute the optimal consumption, optimal labor, optimal next period wealth over the simulation, during the simulation of the capital stock. So where the capital stock is not equal to the steady state capital stock, and our technology level Z fluctuates between 0.98 and 1.02. Our business cycle. So we use again the very same idea. We do not use value function iteration, but Euler equation approach here, solving nonlinear equations problem with the modified Newton-Raphson method. We again start in the last period of life, so where the next period capital stock or wealth is equal to 0, and then go back in age, starting at age 70, 69, and so on and so on. Now our residual function this time, RF here, we need to take care that we have factor prices which are not constant anymore. We are not in non-stochastic steady state. We have a dynamic economy where aggregate capital stock and labor fluctuate, technology fluctuates, and therefore factor prices RT plus 1, pensions, and so on are not constant. So the household has to form an expectations of next period interest rates, next period pensions, wages, and so on to derive his optimal decision. The state vector is now a 6-dimensional one, HS, permanent productivity E, idiosyncratic productivity theta, individual wealth K, aggregate technology Z, aggregate capital K. Now we compute the solution as in the case of the non-stochastic steady state, but now we have to account for the fact that there is a transition probability of aggregate technology Z, which is provided by the Markov transition probabilities prop Z prime given Z. So how does the household in period T compute next period interest rate, next period wage, and so on? So he observes ZT and KT, this period. So he uses the law of motion for KT to forecast KT plus 1. Next, he knows that given ZT plus 1 and KT plus 1, and given that the state is Z prime, so he weighs the utility, the marginal utility next period by this probability here. He also has ZT plus 1, and then he can compute next period labor with the help of this equation. All the variables that he needs to compute next period labor, LT plus 1, are given, so he knows KT plus 1, which he forecast with the first equation, and the transition probability give us next period ZT plus 1, our Z prime here. Now that we have ZT plus 1, KT plus 1, and LT plus 1, we can compute the real interest rate RT plus 1 from the first order condition of the firm, also WT plus 1, and then we can also compute pensions from with the help of the replacement rate. And all these factor prices, pensions, and are used by the household to compute this residual function, his Euler equation, and we search for the root for the value of K prime, which sets the residual function equal to 0. One extra point that I would like to mention, next period consumption C prime and labor supply L prime need to be computed at individual productivity theta prime and aggregate states CT plus 1, ZT plus 1, and KT plus 1. Now we do not have the value of next period policy function for all values of the aggregate capital stock KT plus 1 and individual wealth lowercase kt plus 1. So what we need to do is we use the tabulated values and use interpolation, and because we have two variables, two grids, one over the individual wealth and one over aggregate wealth, we need to use bilinear interpolation. You may also use bicubic interpolation. We have chosen the most simple one here in our case and choose bilinear interpolation. We have to determine a grid for the aggregate capital stock, and we choose 80% that the interval is between 80%, the lower boundary, and 120% of the non-stochastic steady state capital stock K bar, which is equal to 1.818, which we have found in step 1, if you remember. And we choose 8 grid points. We choose few grid points here, 8 grid points, and the reason is that we observe little curvature in the policy function with respect to this variable aggregate wealth K. Of course, we need to check that when we simulate our economy, that the simulated capital stocks remains in the interval 80%, between 80% and 120% of the steady state capital stock. And we have to compute this optimal policy functions at 224,000 grid points. That's the asset space individual plus aggregate asset space that we consider. And this is, of course, again, a time-consuming part. In Gauss, it takes 40 minutes, and in Python, it takes 39 minutes. Step 4, simulate the dynamics of the distribution function. Again, this is a very time-consuming step in the Krusell-Smith algorithm. So we start from an initial distribution and we choose the non-stochastic steady-state distribution and simulate the economy over a couple of periods. We choose 200 periods, but of course you can choose longer time horizons. We also drop the first 50 periods so that the initialization of the distribution makes no difference. In addition, what's possible is that when we choose the initial capital stock to be the non-stochastic steady state, well, this might be different from the average capital stock in the stochastic economy, because in the presence of aggregate risk, for example, households may accumulate higher precautionary savings, and this implies that the average stochastic capital stock is higher than the non-stochastic steady-state capital stock. But we find this difference to be small, so in this application here, it's not a particular problem. But you should be careful if you, for example, use models with higher risk aversion or something like this. Okay, and there are basically two options how we can simulate the dynamics. We can use Monte Carlo simulation. So for example, we pick 1,000 households in each cohort for the 1-year-old, 2-year-old, 3-year-old, deriving 70,000 households and simulate how they behave over their life cycle and over time, and then aggregate these values. We find this too time consuming, especially in overlapping generations. You need a certain number of households, 1,000 or above, in each cohort, so that you can somehow get to the law of large numbers, that these 1,000 households almost behave like they were the whole population. We instead advocate for using a discrete approximation of the distribution at grid points, and assume that you can only get to one of the grid points in the next period by choosing a lottery. We will show you this in a minute. And then just keep track of this distribution at the grid points, the measures at these grid points and how they behave, how they choose next period wells, which grid points they get to. This is much faster, and we find also more accurate for given computational speed. So we advocate for this kind of simulation for the dynamics. Let me get into the details. So this is a little bit more tricky here. We start with an initial distribution F0 for the individual states. So we just keep track of the distribution over the individual state space, HS, permanent productivity E, idiosyncratic productivity theta, and wells K, and period T equal to 0. We normalize each distribution in period 1, 2, and so on to 1. So we divide by total population size. In the initial steady state, in period 0, we choose the non-stochastic steady state capital stock, K bar. And we roll a dice, so a random number generator with probability 1/2. We assume that the initial technology state Z1 is equal to Z1 or Z2. So we have to assign a value in this period Z because we need to compute the transition probability to get to Z prime, Z1 in the next period. And we have computed the optimal policy function, and now we start for each measure of a household with characteristics S, E, theta, and K, we compute his next period capital stock, take his mass, this mass in period 0, and allocate it to the mass in the measure in period 1 with the capital stock K prime. And we keep on, and we do this for all grid points in period 0 and add them to the measures in period 1 So to keep track of what's happening to our distribution and to each individual with measure f at the individual state SE, theta, and k. And of course, we have to consider that next period in idiosyncratic productivity, theta prime is given by either theta 1 or theta 2, depending on the transition probabilities, and allocate the respective shares to these two types. Now, if k prime is most certainly is not a grid point, and then we have to split the measure at this grid point, at this point k prime, to the neighboring two grid points, and of course, the closer it is to the neighboring grid point, the higher will be the share of the measure that this grid point is allocated, and of course, the two measures must be equal to 1, so that all the measure at period t is allocated to the grid points in period t plus 1. And we will get into the detail in the next slide. And we have to consider that only phi s of the agents survive. So only the phi s times this measure will survive to the next period. And we have to correct for the growing population so that 1 plus n, the share of this measure declines by the factor 1 plus n. And we do this for a period of 200, for over 200 periods, and use a random number generator to compute next period aggregate technology Z given current period technology Z. Now in Gauss it's very fast, it's 3 minutes, but in Python it's very slow, it's 1 hour 40 minutes, and I will tell you why in a minute. So let me show you how we compute the dynamics of the distribution. Let's assume we have the initial distribution given by F0, which is our steady state distribution. And now we want to compute the distribution in period 1. We have the predetermined next period capital stock, kt plus 1, because we know what the agents in period t, in period 0, save. Therefore, the capital stock is predetermined. We use a random number generator to find whether the next period technology is either Z1 or Z2, depending on the transition probability of our Markov process. Now, in period 1, when we compute the measure of the agents F1, we know that there's a newborn generation. So the newborn generation has the total mass of mu1, which is a population share of the 1-year-old. And we assume that each productivity, each permanent productivity, E1 or E2, and each idiosyncratic productivity, theta 1, theta 2, is equally likely. So equally likely means that it gets allocated the share of 1/4. So we can initialize the distribution in the next period for the 1-year-old by mu1/4 if for the Wells level 0 at age s equal to 1, and all other measures of the 1-year-olds are equal to 0, because the 1-year-old is born without any Wells. Now we just need to compute the distribution F1 at age s plus 1 for s equal to 1, 2, and so on, up to 69. Now, how shall we do this? Therefore, we look at all grid points s, e, j, theta I, theta k, I, k of the individual asset grid at ages s equal to 1 equal to from s equal to 1 up to s equal to 69. Compute the optimal next period wealth, k prime. And let's assume it's a grid point, ki. Well, in this case, we add we add the measure of the household with this individual state variable to the measure F1 in the next period with productivity theta prime, noticing that we have the transition probability depending on theta in the present period, in period 0, times the measure, times the survival probability, so 1 minus phi as of the people will die, so we only add those who survive. And notice that the share of the agent declines by 1 plus n because population grows. And we do this for next period, idiosyncratic productivity theta prime for the two values theta 1 and theta 2 on our grid. Now this is the case if the next period capital stock K prime happens to be a grid point K1. This will, for example, be the case when the credit constraint is binding. So a lot of people choose next period capital stock, next period wealth equal to 0 because there is a credit constraint. And then the measure will be added to 1 at the grid point. Now, if the next period capital stock K prime falls between Ki and Ki plus 1 between two grid points, we split it up according to these two shares here, which sum up to 1. And the closer it is to the point K1, Ki, the larger will be this share. And if it's equal to Ki, the extreme case, this probability factor will be 1. If it's equal to K1 plus I plus 1, then this probability factor here will be, this factor here will be equal to 0. So we play kind of linear lottery. So with these two probabilities, they end up at either the next period capital stock Ki or Ki plus 1, and at the same measure here to this grid point. Now, this approximation is of course only exact if our optimal savings K prime are a linear function of individual capital stock. So the smaller the finer the asset grid and the more linear our next wealth policy function is, the closer is this approximation that we assume, okay, we split up this measure between the two neighboring capital asset grid points in proportion to the distance to these grid points. Okay, and this step is very time consuming. Why? At each time we have to compute the next period policy function, which is a bilinear, we use bilinear interpolation at the capital stock individual wealths K and aggregate wealths K. And we need to do this assignment here to add up the measures for all grid points. And of course, this takes time, a couple of computational operations, and we have to do this 2.8 million times. So over 200 periods that we consider, each time we have to do it for 70 cohorts, 50 individual wealth grid points, and the 2 permanent productivities and the 2 idiosyncratic productivities. And these loops, they are taking a lot of time in Python. So to have a loop over 5 or 6 nested iterations here, that's what's really slowing down Python and also MATLAB, and other computer languages like Fortran or Gauss are much faster in running such a high number of nested loops. Now step 5 is fairly easy. We just have to estimate the law of motion from the law of motion for the aggregates K and the transfers. So we first have to compute the aggregate capital stock labor consumption bequest by summing up over the individual variables given our distribution F. We have to compute the social security tax rate that balances social security budget. This gives us the labor income tax, the wage tax, so therefore we can compute aggregate taxes, and from the fiscal budget we get aggregate transfers as a residual, and this will be used here in our OLS regression of the three aggregates K, L, and transfers on capital stock and technology level. So our regression here in step 2. So we have just simulated these time series here for capital stock, labor, and transfers, and now we have to use ordinary least squares to estimate these coefficients omega here. So that's very fast, and we get very high R squared equal to 1. Once we have computed it, we update our coefficient. We use a 30% update here for these coefficients omega, and we iterate until these coefficients converge so that the omegas, the absolute difference between omegas in two iterations are less than 0.001, and then we stop. So in total, we need 23 loops in this outer loop over our policy function, over our parameters omega in the functions jk, jl, and j transfers. Total computational time, as I mentioned before, is 5 hours in Gauss and 2 days in Python. Now we test the goodness of fit. R squared is equal to 1 in all regressions, and there's a discussion of this measure of fit, of the goodness of fit measure R squared in Herrn Mausner. There are some arguments about this R squared. I will not get into the details here. Please check chapter 3 in our book. All right, so this describes our Krusell-Smith algorithm, its implementation in Python or Gauss, and the simulation step here is really time consuming in Python because of this nested loop. We have iterate over 5 different variables here. And the policy function computation is also time consuming because policy functions are computed at 228,000 grid points, which are the grid points of both individual and aggregate states. And of course, when we simulate the model, we can also keep track of the income shares and compute the correlation with GDP. That's what we have done in this result table. We applied the Hartree-Prescott filter to the income shares and to log GDP using the smoothing parameter lambda equal to 100 in our Hartree-Prescott filter. So standard way to use for annual data here. To compute this for quarterly data, you can imagine that computational time goes up by a factor of 4 because we have to increase the number of simulation periods here. Now let me again emphasize to you where you can download the Python and Gauss codes on our homepage, where the address here is given in this link, www.uni-augsburg.de. And if you have problems finding this code or problems experienced downloading this code, you can also send me an email to burkhard.herr@wiwi.uni-augsburg.de. Or if you have comments, questions with regard to the algorithm, I will be happy to answer your questions or get your comments. And thank you for all your patience, and I hope this Krusell-Smith algorithm may become an integral part of your research or your computational techniques in your PhD paper.